And here we have we try to calculate the force and moment acting on an arbitrary shape of body by means of a contour integral. Okay, and so we have a flow over the spatial object here, any arbitrary object here. And I can show you the final result for this integral, velocity integral law, and for you to understand easily. Okay, here is one of the final equation you will use most of it. Okay， 就是唯一这个公式你会用到最多的，前面这只是证明而已。All this is just proof. Okay, and here you find out this. Okay. So this is the process one of equation for the process integral law. So if you want to find the force in x direction and force in y direction acting on this object, this is x direction and y direction. Okay. And we have the force acting on the object here. And how do you find out this force x and the force y? We can substitute by using this equation. Okay, this equation, the W is what? W is our previous compressed velocity. Okay, so once we know compressed velocity, okay, and we take a square root of this, and then take a integral along the closed loop. Okay. Sorry about that. I turn off my. Okay. So that will become very easy, right? We know how to return the compressed potential. From compressed potential, we know how to derive the compressed velocity. Just take the derivative df dz. And once we know the compressed velocity here, and we substitute into this equation, we can find out what? The force acting on this object. Okay, force acting on this object in x direction and y direction. Okay, it's corresponding to real part and imaginary part. Okay, and the second equation here is what? Second equation is the moment. So we have two equations. Plus integral law has two equations. One of the equations is I just show you here. And second equation, the moment. We can also find out what's the moment. Moment means the turning torque, right? Turning torque acting on this object when the flow over this space arbitrary shape of the body. Okay, so here is the equation you will. Okay, here equation you will use. We take instead of w squared like in the force, we times z times w squared, and also take a closed loop integral of this, and then after that we take a real part and tie a constant. This it will give you the moment, okay, acting on this object. Okay, so eventually you will using these two equations to find out, okay, your force in x direction and force in y direction, as well as your moment. Okay. Once you find out your compressed velocity. Okay, so that's how powerful of the process integral law. Okay, 那用这个定理可以去解决计算，给流体流过一个东西，它这个东西流体作用在这个东西上面，作用在这个物体上面的力量 ，x 方向、y 方向跟它的力矩。Okay, so we will go back to the basic here. Okay, and before we go into the basic here, okay, we have to kind of review a little bit. In undergraduate, we have the control variant analysis. If you remember, what's the control variant analysis? I try to get one example from your undergraduate book. Okay, if I have here, I show you one of your undergraduate book. Okay, has this kind of physical problem. Okay, 从你们大学部的课本里面，我抠了一页纸。起来，让回忆一下你以前所学的。Okay, this is one of undergraduate course you may have. Right? This is one of undergraduate course you may have before. Okay. This is one of jet, okay, acting on this object, okay, and jet impinging on this surface here, divide into two strings, upward and downward direction. And you try to find out, okay, try to find out the horizontal force acting on the support, okay? And how do you calculate it? We have to take a control bearing, right? So if you take a control bearing here and here, for example, if you do that, okay, and then why the flow will be turned? Because we have this object will have an acting force on this fluid, so force this fluid to turn, right? 所以这个流体为什么会转弯？为什么？因为我们的物体对这个流体对这流体是个力量。So if you take your control bearing here, for example, control bearing here, and try to find out the force this object acting on this, okay, this flow, right? And then the force acting on this flow will change our momentum. And momentum we can calculate inlet momentum and outlet momentum in x direction. Okay, the change of x momentum give you the force in x direction, right? So here, if you remember, this is Rx. Okay, Rx, and for this case here, we have inlet corresponding to sign convention. Okay, 就是符号的定义的话 for the inlet is negative, right? For the outlet is a positive sign. So here is a negative. Okay, negative what? That you have a mass flow rate is equal to low AV. This is A here, for example. Instead of here, we just define our A is here. So low AV times what? Times U velocity. Okay. So here we have a low AV times U velocity is a x direction momentum. Okay. And for the outlet here, we don't have any U velocity because we only have a V velocity, Y direction velocity. So we only have this, and we don't have outlet. So only the X direction force will give you like this. Okay, it give you like this. That's how you calculate. So we were using a similar control bearing term to calculate our using our Blasius integral load. Okay, if you remember this, so we will return to our Blasius integral load here. Okay. So in order to find out the force acting on this object, okay, we can find out the vice versa. We can find out the object acting on the flow, right? Only the direction is different, right? One is just negative sign, okay. Take a negative sign. So we can have a control bearing on the fluid itself. So we take a control bearing like this. This is our control bearing. This is one of control bearing, and then we cut into here and cut that. So this is our control bearing. So all these control bearing represent what? I'm sorry. I take the control bearing like this. Okay, should be like this. This is on one of the control surface, and then go out. Okay, and then here, and go in. Okay, that's a control bearing. So inside this control bearing here, we enclose a fluid only, right? Inside here we have only fluid. The boundary already excluded by when I take this is a control surface here. Okay. So our closed loop contour C, okay, including the CO. This is CO here, okay, outside of the contour. CI is here, and since this contour one is in and the other is out, so these two contour will be cancelled, okay, because just one time is downward, one time is upward, so these two contour will be cancelled. So our C, if you take a C, okay, later if you take a C, okay, the contour integral, you will find out, okay, later. And then, so we were using the so-called control bearing analysis. And control bearing analysis is equal to what? Let me show you, okay. Okay. So this is one of the complete control bearing integral along the whole surface here. As you can see, minus x is a force acting, this object acting on the fluid. This is minus x. Since x is what? X is a fluid acting on our object. And the minus s becomes what? This object acting on fluid. Okay, so this is force for the object acting on the fluid. Minus p dy. P dy is what? We integrate all this surface here. Okay, p dy give you what? The force in what? In x direction. You can see this is a dy here, and p dy is only this direction, right? The force in x direction. So this is force due to the pressure force in x direction. And that will give you what? Give you these two. Okay, we have the momentum into and outside, in and out of this control surface. We have two control surfaces. One is the CO, the other is CI. CO represents this control surface, and CI is this control surface. Okay. And this term here is usually familiar. As you can see, rho times u dy. Rho times u dy is here. This is dy here. So u dy is what? U dy is outward direction. So outward direction is the positive sign. Okay? And v dx, v is this direction. V dx what? Is into our control boundary. When into the control boundary is a negative sign. Okay? So this is represent all the mass flow rate. Right? Mass flow rate into outside of out from the control surface, and times our velocity. So this gives you the momentum in the x direction. Okay, so we have a CO and CI. So we have this contour and as well as this contour, and these two should be cancelled because if you integrate this and this, it should be cancelled. Okay, so let's give you the what? The full control boundary. Okay, integral equation. Okay, similar to your undergraduate. Can you follow it? 这个跟你们大学不一样，只是写成怎样？写成我积分的这个体积是由这个 CO 跟 CI 配上这两条 ，OK， 所以我的 control surface 是这样子绕过来，这样子出去，这样 ，OK。So this is a control volume form for your momentum change in from the control volume give you the force acting on this fluid. So here is a CI. CI is inside this boundary here, right? This is our object. So CI is a straight line, as you can see, right? Potential flow boundary is a straight line. Okay, so this is straight line. So there is no momentum across the CI, right? Because the flow it cannot across the CI here. Okay, so this is a momentum across the CI here. This should be equal to 0. So this should be equal to 0 for this CI integral. So only term we have is only outside contour for this CO here. So this equation, this is integral equation reduced to this because this CI integral equal to 0. Okay. So this is x direction. Okay, this is y direction. We can also, once we replace u to v here, we can find out the y direction force, and this is p dx. Okay, and moment just you have a force times what? Times a arc, right? Arm of force. Okay, 就是力量乘一个距离。Okay, so give you the torque. So this is a momentum times force times a distance give you the torque. Okay. So that will be the force x, y, and m. So can be written like this. This is from the control boundary, integral equation. So once we have that, you can see we can have this and this and this through the control boundary. So we can return to this one. This is just so our x, right? X force will be equal to this. Okay, we just kind of rearrange our equation, become like this, and our y. Force will be equal to this. And this x and y will be what? Become the force acting on the object, right? 对，这个地方我们变成是 x 就是的物理意义就是流体作用在这个物体上面的力量。当有个流体流过去这地方的时候，它作用在这上面的多少力量 Okay, so this is the equation we would like to have. Okay. Here, okay, we assume this is steady state flow and there is no body force. So we have the Bernoulli equation. Bernoulli equation reduced to this. Okay, this is a Bernoulli equation. So P plus 1/2 rho U squared and plus B squared, okay, is equal to a constant. Okay. So from this equation, as you can see, we can modify a little bit, become like this. Can you see the difference? Okay, here we plus this, okay, and here it become nice sign here instead of positive sign here. Okay, so similar here. So we can, from this equation, we can modify. The reason I would like to use this formula later. Okay. So as you can see, P and the rho U squared can be summed up together for this integral. This is dy integral. So dy become P plus rho U squared here. And we take a minus outside this bracket. And the rest of term is rho UV dx, right? And P plus rho U squared here can be replaced by using the Bernoulli equation. We can find out this. This is a Bernoulli constant plus this, so the Bernoulli constant plus this, okay? And then as you can see, when you have Bernoulli, this is constant. When you do the closed loop contour, what happens? It's equal to 0, right? 当你一个定值做一个封闭曲线的积分，这个定值就会等于0，对不对？终点一样。Okay, so this will be disappear. The only term left is this term here, okay, and plus this term here. So we have only this term, okay. Because the B is through the integral, closed loop integral, this constant will be equal to 0. Similar to the Y, okay, force in the Y direction, we can replace this rho P plus rho V squared by using this formula. This formula is from what? It's from Bernoulli equation. Okay, it's from Bernoulli equation. So we just replace like this, and then become using the Bernoulli equation. We can have this form here. And again, B can be, through integral, B will disappear. So our formula will be reduced to this. Since our B for this is for this two integral will be equal to 0. Okay, until here is just mathematics, right? It is pure mathematics. Okay, 所有的就是简单的数学。Okay. So we have the x equal to this and y equal to this. So we can start from here. X equal to this, y equal to this. That is from this here and here. We just copy to here. Okay, 我把它抄过来到这里来。Okay, so this is a one we just have here. It's x equal to this and y equal to this. Okay, and let's do kind of reverse engineer. Okay. What do I mean reverse engineer? 我们从它的 Brownian integral law give me this solution form. This real part is equal to x and imaginary part is equal to y, right? So we just try to find out this is true or not. Okay? So we just do the reverse engineer, and reverse engineer is what? W is equal to u minus iv, right? This is the compressed velocity, okay? And square. And dz is equal to dx plus I dy. So if you do that, okay, take this integral here, and you rearrange, okay, this integral and become real part and imaginary part, real part and imaginary part, and you can find out for this real part, compare with our x here, this one should be what? And here, what happened? It's the same, right? This one and this one is the same. So this give me the x. This give me the x. And how about this imaginary part of this? Compare with this. Only what? Only the. Okay. Only the sign is different, right? Sign is different. This is a positive sign. This is negative sign. Low is here. Low is here, right? Low is here. Okay. So this is become x minus iy. Okay, so that kind of proof. Okay, for this formula here, x is force in x direction minus iy, y is a force in y direction. Okay, how do you get this? You can get this from this formula. I times rho over 2, okay, the closed loop integral C sub 0 and W squared complete velocity squared dz. And if you can find out this, you can find out real part is represent the force in x direction. And imaginary part equal to minus y is a force in the y direction, but the reverse direction, reverse sign here. Okay? So that's, we proved the first equation for Bloch's integral law. And second equation, moment. Moment is very similar, okay? We can do the moment, this is a moment, okay? And this is a closed loop control borrowing, okay? For this, okay? If you do the control borrowing, you are able to find the moment through a control borrowing analysis. We can find out this equation. Okay, so moment, this moment, we rearrange this equation. Moment should be equal to this. Okay, so everything this, okay, this turn to the move to the right hand side equation, and this, so this is this term plus this term minus this term here. Okay. Okay, so we don't want to go to the too much detail, but very similar. Okay, what do is we just rearrange it. Integral dx dy, okay, together. This is dx dy part, okay, and dx dy part here you can a similar term p plus rho v square and p plus rho u square here, and these two can be represented by Bernoulli equation. Okay, Bernoulli equation give me this is original Bernoulli equation, but the p plus rho u square through this you can find out it should be equal to this p plus rho v square should be. So again, we replace like this, and this b and b through the closed loop integral, this b will be cancelled. So we have only these two terms, these two, okay, and these two terms left in our integral form. And then, what should we do? Okay, we kind of try to find, okay, we take a common factor out. 我们把这个共同的参数拿到 integral 的奥面。Integral 的外面来 okay, we rho over 2 is a common factor here. Okay, so this common factor can take out from this, okay, integral form. Okay, so eventually we have this one and this one, right? This one and this one. Okay, so this is this integral. This integral will give you the moment. Okay, so again, we try to do is what we try to do using the reverse engineer. Okay, reverse engineer. This is we just find out that our moment should look like this. Okay, so our W is our complete velocity. Complete velocity equal to U minus IV, and W squared is equal to this, right? And if you do for this equation here, we should have the Z times W squared and take this closed loop integral. So Z dz will be Z is this, dz will this. And if you multiply these two, become like this. And so you multiply our W squared, right? This is W squared, okay? Sorry. Wait a moment, okay. This is W squared, right? This is W squared. W squared times what? Z dz, right? Z dz, okay? So Z dz here, as you can see, we have the W squared, there's a real part here, imaginary part here. And Z dz here, we have a real part here, imaginary part here. Okay? So we just take what? We just take for this one here, okay? This is, for this one here, okay? Represent our moment for this term here. So this term here give you what? Give you the real part of the W squared times real part of Z dz. So if you take this multiply, okay, for real part of this is this, right? Real part of this, and real part of this is this. It will give you this term here, okay? 所以你把这个实部的这一项 W squared 的实部跟 Z dz 的实部两个相乘，就会得到这一项 ，okay? So here is the first one, and the second term here, second term for our moment here, you can find out is equal to imaginary part of W squared times imaginary part of Z dz. Okay, and take the minus sign. You can get this term here. So finally, okay, for our moment here, okay, the moment equal to minus rho over 2, minus over 2. Take a integral, closed loop integral with a contour C sub 0. So this term here is equal to this, okay, this here. And this term here equal to this minus, okay, for this imaginary part times this imaginary part. Okay, and then finally you can get it what? You can get this one, okay, will be eventually become like this. Real part of W squared. Okay, I don't know. Can you see this? This real part times real part minus imaginary part times the imaginary part will give you this. Can you see the reason behind this? 你可以发现这个地方的。You can see our, okay, if this, actually using the very simple, okay, a plus ib, this is our first term, and x plus iy is the second term here, okay. So for this term here, take w squared, okay, this is w squared, and this is z, okay, can you see that, okay. So imagine, if you take the real part of this, as you can see, real part of w squared z dz, right? Z dz give you what? This times this is ax, right? This times this give you the minus by, this is real part. So this one, and this one minus this one, right? This is the real part times real part minus imaginary part, so equal to real part, please. Okay, there's only this circumference. Okay, so this is the real part of this one times real part of this one. Okay, minus here, imaginary part of this one times imaginary part of this one. Right, give you the real part of this. 对吗？就是复数里面，它就这样算出它这个 this one, the real part of this one should be calculated by this way. Okay, so once you get this, okay, so we can take the real part of this factor outside of this bracket, and finally we can get our Bar's integral law, the second equation. If you want to find a moment, okay, and it should be look like this. Okay, I think I overtime a little bit. Okay, we should stop here. Okay, 我们大概超过了10分钟，没注意到。Okay, we take a 10 minutes break. Okay, and during the break you can take your homework back. Okay.